Welcome to another unit in business mathematics. This time I'm talking about poles and discontinuities, or rather, mostly it's different types of discontinuities, whereas poles are one type of discontinuity. And well, before we actually can talk about discontinuities, we first need to know what continuity actually means. In this context, we can ask the following question. What does continuity actually mean? Well, if we want to answer it, we actually have two possible approaches we can follow. A more mathematical and a more pragmatic approach. More pragmatic approach is relatively straightforward. If we want to know whether a function is continuous, especially in a specific point, we simply test if we can draw this function without having to lift our pen. If this is possible, then in the area where I actually can draw the whole function without lifting the pen, the function is continuous. If I have to lift the pen at one point, at this point there's a discontinuity. Well, the nice thing about this approach is it's pretty close to the mathematical one. In a mathematical context, what we say is we consider two limits. The limit from the left and the limit from the right. So we get closer and closer and closer to our specific point here, x0. And if we are infinitesimally small with the distance to this point, and both of these values we get as a result in our function f of x, then we can say it's continuous. If those values we get from f of x are actually different for the left-sided and the right-sided limit, then we can say it's not continuous. And well, to give you illustrations for discontinuities, we can actually discuss 5 different types of discontinuities, whereas two of those we have here are more or less the same. And the fifth and final one, we're not going into detail here. And well, the 5 times we have is, first off, we can have so-called poles. Poles means if I have a pole, for example, at 0, that if x gets closer to 0, the functional value increases continuously. So more or less moves towards infinity or minus infinity. And here we actually have two possibilities. As we said before, we have the left-sided and the right-sided limit. If the left-sided limit goes to the same infinity as the right-sided one, so for example, both go towards plus infinity, we call this a pole without a sign change. So for example, with this function here, if we get closer and closer to 3, in both cases, this function will go towards plus infinity. The opposite possibility is we actually have a sign change. So one side goes towards plus infinity, the other side towards minus infinity. Let's see here poles with sign changes. That's something like this. We have a gap in the domain at minus 1. So if we get closer to minus 1, depends from which side we are actually coming. As our denominator can get positive and negative, so in other words, if we go from the right, so we insert, for example, 0, then we get something positive. If we get there from the left, for example, minus 2, we get minus 1. So it's negative. So if we go towards this gap from the left, we approach it from the left, we move toward minus infinity. If we move toward this gap from the right, we move toward plus infinity. So this is a pole with a sign change. And well, question is, how does this look like? That's what we actually can see in this figure. Here we see the values get closer and closer and closer to the specific functional to the specific gap in the domain. In the first one, it's 3. In the second one, it's -1. And we can imagine this as if at this specific point we have a vertical line and the function gets closer and closer to this vertical line. It never reaches this vertical line, but it gets increasingly closer. That's what we call poles. If we were to have the same effect, but turned by 90 degrees, we would call this an asymptote. There's something like this as well. Well, the first one wouldn't actually work out, but the second one could actually work out, and we would get something similar here in the second one as well if we consider 0. In this case, with 0 as functional value, we have an asymptote because our function gets closer and closer to 0, but will never touch 0. So asymptotes are just basically similar to poles, with the exception that they apply to the x-axis, whereas poles apply to the y-axis. Well, with those two types of discontinuities out of the picture, let's move on to the third type. The third type are so-called removable gaps. A removable gap isn't really a discontinuity, because if we move there from the left and the right, we will still get the same value, but it's still not allowed to insert this particular value into our function. If we consider, for example, this function here, we see directly we are not allowed to insert -6, because in this case the denominator would become 0. But if you look closer, you see that the denominator actually is more or less like a third binomial form, which would translate into x plus 6 times x minus 6. Now we can shorten out the x plus 6. So this function could reduce to x minus 6. And in x minus 6, I'm allowed to insert -6. So this function actually looks like this. With this one speciality, I'm not allowed to insert -6, so I have this removable gap, which we marked here with this specific point, at x equal to -6. So this is, well, not continuous, because I have to lift the pen, but it's not directly following the mathematical definition of left-sided and right-sided limit need to be the same. Because if I get closer and closer, both of them approach it, but I'm still not allowed to insert this point. A bit more critical is the fourth and final aspect we discuss here. The fourth and final discontinuity we have here are steps, or rather a stepwise defined function. So we have different parts for the x values, which each have a functional description of their own. For example, in this case, we have constant functions, but different constants for different x values. And if we illustrate this graphically, we can see that they do not connect with each other. That's actually the problem. Well, if you have, for example, different functions, not necessarily does this mean that the resulting stepwise function is discontinuous. It could be if you do not take care that at the points where the different intervals actually meet each other, that the two parts of this function actually show the same functional value at this point. If you account for this, you will get a continuous function. Everything works out fine. If we have something like this here, in particular if you have constant functions, actually if you go from the left In this case, you will always have a smaller value at the critical points, so 2, 4, and 5, than as if you approach it from the right. Well, this is something which occurs, for example, in statistics if you go with discrete density functions, or more or less probability functions, like with histograms or even with the distribution functions. This will look more or less like what we have here. And well, that's like the fourth and final type of discontinuity we have here. We could have something else as well, but this would be a bit more problematic to actually illustrate this, where the problem with this actually resides. So I'm just mentioning as a final step, it's a function like sinus of 1 divided by x. You see directly there's a problem at 0, but the problem is different than what we had before. I will finish at this point, so let me just say I hope you enjoyed this session up to this point, and I say goodbye and see you next time.